All right, so let's now get started on today's meeting. So last week, just to kind of put this all in context so you can see what we're building, last week we started our look at the normal distribution with normal distribution part 1, followed up by normal distribution part 2. And then today we're going to continue on with our look at important distributions for statistics. But now we're going to take a look at sampling distributions. And just to give you a little bit of foreshadowing, sampling distributions are like the inception of statistics. So it's almost as if we have this normal distribution, and then from that distribution, we're going to go even deeper into a sampling distribution, and then there is one layer even deeper than that in terms of these distributions. So just to kind of put it on your radar, we're going to be working with 3 different distributions very, very soon. So it's very important to remember which ones you are talking about and using. Is it the normal distribution of, for example, a population of scores? Is it a sampling distribution, which we're going to take a look at today? Or is it a distribution of sample means, which is what we're going to look at next time? So we are now doing a little stats-ception, and it's very important to keep those separate. And we'll start doing that with today's look at sampling distributions. And also today is going to be one of the first times that the inferential nature of statistics is going to be made very evident when we talk about inferring certain things about a population, that is parameters, from things that we know about a sample, specifically statistics. So we'll discuss that today as well. And then we're going to continue on with our ComRom as we use and revisit some online resources that allow us to visualize these sampling distributions. So we are going to dive into it, get right into it today when we take a look at sampling again, but this time specifically with the idea of building up not just a single sample, but a distribution of samples. And we're going to see exactly what that means when we take a look at sampling distributions. And before we get to all that, as promised, we are going to finish up our look at the normal distribution by taking a look and finishing a look at the day in the life of an educational psychologist as they visit various schools and solve problems for various deans and superintendents of those schools by using the properties of the normal curve to make plans, make predictions, to use the resources of that school as best as possible to service as many students as possible. So we're going to begin now with some do-it-with-me demos. However, these are going to be gone through at a little bit of a quicker pace. Hopefully you've had a chance to try some of these at home. So it is going to be a little bit quicker than our normal pace, but hopefully it'll all make sense to you. You've tried it at home, and now we'll just fortify that knowledge and those skills. All right, so again, on the plan for today, they should say sampling distribution part 1, but we're going to continue on with your day as a director of counseling psychological services by taking a look at student depression rates and a very interesting study on optimal levels of student stress, which not only considers optimal levels of stress, but also considers what kind of stress are students under. And then this will all be illustrated with some do-it-with-me demos. And then we're going to just have a small little public service announcement to remind you that while a lot of things in our universe are normal, oftentimes, especially in psychology, things are not normal. So we'll take a look at a few important examples just to illustrate that idea. And then we'll get to the meat of what we're doing today, which is sampling distributions. We're going to talk about parameters in statistics, which is at the heart of inferential statistics. And then we'll end with our look at bias and variability, which are 2 qualities that a statistic has that we want to minimize both of those for the best inferential power in our statistics. All right, so you might recall that last time we were taking a look at a day in the life of a educational school psychologist. So we basically had a lot of challenges and projects that were done. So you were in the role of this school psychologist visiting various deans, and they were asking you things like, how many at-risk students do we have according to the relationship assessment scale? And then also what score on that relationship assessment scale would give us the top 10% of students who are thriving in relationships? And then another dean wanted to know, well, how common is sleep deprivation among their students, given the fact that students sleep on average 6.5 hours with a standard deviation of 1.2 hours, but less than 6 hours has been shown to be detrimental to cognitive ability and learning. And then we also took a look at a superintendent that was trying to organize their gifted programs and remedial student programs. So we wanted to know how many students did they need to plan for, if the criteria for getting into the gifted program was an IQ of 120 and more. And then we also did a very complicated multi-step use of the normal curve, where they wanted to know what are the minimum and maximum IQ scores for remedial program students. If the maximum score is 1/2 of a standard deviation below the mean, and then we had to figure out the minimum score, given that there were only 50 seats available in this remedial program. So those are the ones that we covered last time. So let's get into the new ones here. So let's set it up with a little bit of context. So you are a school counseling psychologist, and you've been called into a large university. The dean has called you into his office to discuss next year's budget. He leans back in his chair and says, I don't see why we should be investing more money into student counseling. Depression is rare. Maybe a few students need help, but most are doing just fine. You know that isn't true. Decades of research show that college mental health problems are both common and consequential. The consequences are real. Untreated depression is linked with poorer grades, higher dropout rates, and even unaliving risk. Target campus counseling programs have been shown to improve not only emotional well-being, but also academic persistence and retention. So there's almost nothing but upside to college mental health programs. So investing in counseling is not just about mental health, but it also impacts student success. Incidentally, just as an aside, this is a very, very good example of how in the real world, if you're trying to convince somebody to do something, to implement some sort of plan, implement some sort of project, you don't want to convince them about the benefits of the project that are important to you. You want to convince them about the benefit of the projects that are important to them. So for us as psychologists, mental health is probably going to be our number one priority. And we're going to go to any university and we're going to say, hey, this program will help the mental health of your students. And that is nowhere near as convincing to a dean than telling them this program will increase the academic success of your students, because that's what they care. Now, it's the same program, but this is just a little aside. When you're trying to convince people, find out what they care about and frame your solution in terms of that characteristic that they care about. All right, so we get to that point. It's about student success, not just about mental health. The dean, however, wants numbers. He crosses his arms and he asks, well, what percentage of students have at least moderate depression? So what percentage of students need some sort of counseling? So you turn to the data from national studies. You know that the scores on the Beck's Depression Inventory for college populations typically average around a mean of 9.4 with a standard deviation of 8.45. So clinically, a score of 20 or higher indicates at least moderate depression, the point at which students would strongly benefit from counseling. So now we got to figure out, well, if that's the case, if the Beck's Depression Inventory for college students has a mean of 9.14 and a standard deviation of 8.45, and moderate depression is defined as Beck's Depression Inventory score greater than 20, what percentage of students actually fall into that category? So there's our challenge. First thing we're going to do is we are going to draw it out. So hopefully you're becoming much more familiar with how normal curves work, but I still highly recommend still draw it out. So we have our, keep trying to draw on the main screen. We have our x-axis here, and we have our normal curve up there. And then we want to draw the mean typically. So we got our mean right down here. Remember that the mean on a normal distribution is at the highest peak, cuts the normal distribution right in half. Normal distributions are symmetrical. So we have our population mean from the research, and that is 9.14. And that is right there. And then we know that Beck's depression inventory says that moderate depression starts at a score of 20. So this is 9.14. Scores this way are lower than 9.14. Scores this way are higher. So we want a score of 20. So that is that line right there. Again, it does not need to be at all scaled or accurate in any way, just so long as it's on the right side. And then finally, we want students that are higher than a score of 20. So we are interested in these students over here on this distribution, students that score higher than 20. So we color that in, and that's going to keep us from making any mistakes, and it'll allow us, importantly, to unload all of our cognitive energy into figuring this question out rather than using our working memory to try to keep this information in our working memory. All right, so once we got that, we're going to go to our online application right here. So this is the Staplet normal distributions application. So we want to choose from calculate an area under the normal curve versus calculate a value corresponding to an area. So we can check back with our picture here, and we know the value. The value here is 20. So we don't got to calculate a value. We want to know what this area is. So we choose area under the normal curve. The mean is given to us. The mean score for the Beck's depression inventory is 9.41. The standard deviation is also given to us, and we need that information if we're going to use a normal distribution. We can then plot the distribution, and then we want to calculate the area, and we have four options here: between two values, to the left of a value, to the right of a value, or outside a region. Once again, just double check. We want to the right of a value. We want that area that is to the right of the value. So we go back and we choose to the right of a value. And then the value that was given to us was 20. That is the cutoff for moderate depression at least. So we calculate that area, and we get an area of 9.94%. So 9.94% of our distribution falls into that colored in tail. 9.94% of our distribution falls into this blue area here. And what that means is that 9.94% of college students have at least moderate or greater levels of depression. So we can now go back to the dean, and we can say, well, we just did the calculations, and the percentage of students that have at least moderate depression are 9.94%. So it's not rare. It's basically 1 out of every 10 students. So that is the percentage of students that have at least moderate depression. So let's say that the campus counseling program is developed, and it will help students with mild to moderate levels of depression. So we developed this program, and it will help students with mild levels to moderate levels of depression. Students below mild levels don't need the program, and students with severe amounts of depression need to be referred to a professional. But on the school's system in their program, we develop a program that will help students with mild to moderate levels of depression. So now we want to know, well, what percentage of students is that going to be? So again, we're dealing with the same Beck's depression inventory, same mean, same standard deviation, but now we're looking for scores that are between 14, because that's the cutoff for mild, up to 28, because that's a cutoff for moderate. Beyond 28, you're into severe amounts of depression. Below 14, you're into no amounts of depression. It's below mild. So we want to know, well, how many students are we talking about between 14 to 28? So once again, this one is going to be that multi-step one. So the first thing we need to do is we need to draw it out. So we draw our distribution. And I would also highly recommend, if you are doing this pencil and paper, do draw a new distribution over and over and over again. I have seen students in the past try to use the same distribution, but just kind of shade a different area. That is inviting mistakes into your life. So paper is cheaper than mistakes, especially when we're dealing with students and depression. So draw a new one out. So again, we have our distribution right down the center. That's our mean, 9.14. And now we know that we are, again, not going to the left because those are scores that are less than 9.14. We want scores that are greater. Specifically, we want to know the cutoff for, the area between a score of 14 and a score of 28. So we want to know what is the score of 14, between 14 and 28. So again, we draw in that area. Right there. And as you recall last time, even though it does, actually, you know what? I am kind of new to this applet. Let's see if it'll actually handle this. So we want to calculate the area. That is once again what this tells us. We have values, we need to calculate that area. Let's see if we can do it. So calculate the area between two values. Oh, wow, okay, it actually handled that. So this used to be a multi-step way, and you can do it a multi-step way. And I fell into that strategy because if you use the tables at the back of your textbook, you need to do it this multi-step way. But in this case, we just need our left boundary. So we go back to Excel here, and PowerPoint, we see our left boundary here is 14, and we need our right boundary of 28. So we have our left boundary of 14, we have our right boundary of 28. We calculate the area. That is way easier than that multi-step process. We calculate the area. I would always highly recommend, once you get this drawn, just do a quick double check that that's what you drew and it's actually doing what you asked it or what you thought you asked it to do. So this matches the category of what we drew, so we're all good. So we now have 26.98%. So we can go now back to the dean and we can say, well, hey, we did the calculations and the percentage of students that have mild to moderate depression are 26.98. So almost 27% of students, over 1/4 of your students are going to benefit from this program. And it could actually increase their academic success and mental health if we implement this program for mild to moderate levels of depression. All right. So we're done with this, Dean. We've answered his questions. So now we're on to our final appointment. And we have one last meeting. So we're meeting with the dean of students at another university, and the dean looks doubtful. He says, students keep saying they're stressed, but maybe stress just means they're being pushed to perform. Isn't some stress good? So you nod, he's partly right. Research shows that not all stress is actually equal. So according to the challenge hindrance framework, and this was proposed by Searle and then I think more later developed by Lee et al. Some stressors like exams, projects, or tight deadlines can be appraised as challenges. So these often motivate effort and lead to growth. But other stressors like unclear rules, red tape, constant interpersonal conflict, these are seen as hindrances, blocking progress and consistently harming well-being and performance. So there's two types of stress. There actually is stress that we appraise or view as challenges, and those ones actually push us to perform at higher levels. Then we have other stressors that are seen as hindrances, which actually decrease our ability to perform and decrease our well-being. So what you would want to know if you are ever dealing with the question of stress in a certain environment, for example, at a university, you always want to measure both of these. What kinds of stress and how much of each are being experienced by students? So we take a look at some of the research that's been done on this. And if this is measured using the threat appraisal, challenge appraisal scales that were developed by Malkoch et al. Challenge appraisals, they have, for college students, they have a mean of 3.48 on a 1 to 5 point scale. And threat appraisals have a mean of 1.98 on a 5 point scale. So those are the means that we have. And what the dean wants to know is, well, how bad is our situation in our schools? Specifically, how many students do we have that are actually in beneficial zones levels of stress? So that's where we start, again, taking a look at some of the data that's been done previously. And what has been found is that for challenge appraisals, for obstacles, stressors that are viewed as challenges. So these are the exams, projects, the tight deadlines. For challenge appraisals, the mean, again, on a university would be 3.48, standard deviation of 0.81. And that beneficial zone would be 4.0 out of 5. So what we want to know is how many students are in that beneficial zone, getting stressed enough in a challenging way that their performance is actually increasing. So once again, we go back. Once again, we start drawing poorly. So we have our normal distribution here. And we have that mean of 3.48. And we have that beneficial zone of 4. So let's say that 4 is right there. So how many students are experiencing stress levels that are greater than or equal to 4? So in this distribution here, these are all the students that are less than 3.48. These are all the students over here that are more than 4. Those are the ones we're interested in. So we color in that area, more than 4. And that is the area that we're looking for. There we go. All right, so now we have our information. We go back to our distribution. We remember to change the mean and the standard deviation. So when you change your question, make sure that you update that mean. Otherwise, your numbers will be wildly off. So we have a mean of 3.48. We have a standard deviation of 0.81. So we plot that distribution. We want values to the region to the right of a value. That is what we drew. We want that region to the right of 4.0. So we go back here. The value we're looking for is 4. We calculate that area, and we see that 26.04% of students are in that beneficial zone. So 26% of students are being stressed in a challenging way, in a positive way, and then that means that the rest of the students are not. So in that case, we would come here to this dean and we would say, well, 26% or 27%. What was it? Just over 26% of your students are being beneficially stressed. So if they wanted to increase that, they would want to increase the amount of stress that students are under, but importantly, the amount of challenging stress that the students are under, stress that they see as motivating. So then the other question becomes, well, now that we know that 26% are in this beneficial known for challenge appraisals, well, what about the other appraisals? What about the hindrance appraisals? So studies have shown that the average hindrance score for threat appraisals is a mean of 1.98 with a standard deviation of 0.87. And let's say that the beneficial zone for threat appraisals is less than 2.6. So we don't want threat appraisals to be high. We don't want those stressors to be high because those stressors are actually impairing performance. So we once again, we don't go there yet. We got to draw first. So we're drawing the same distribution. Actually, no, sorry. We're drawing a new distribution. This one has a mean of 1.98 because this is the threat appraisals. So we got a mean of 1.98. All right. And then once again, going this way, scores that are lower than 1.98. Going this way, scores that are higher than 1.98. We want 2.6. So let's just say that's right there, 2.6. And then we want who is, oh, I almost made the mistake. We want who is below 2.6. So usually we would just want this little section here that I almost colored in. We don't. We want everybody that is less than 2.6. So that is all of these people. So this is another good reason why you want to draw this out. First off, I almost made that mistake because we got so used to just checking the right tail for students that are scoring more. We didn't notice we want students that are scoring less because these are the ones that are in the beneficial zone for the threat appraisal stressors. So this is the area that we want next. So we draw that in. And then also when you draw stuff in like this, it lets you just double check the math. Just double check the math a little bit because we know based on what we've drawn here that we're going to be looking for a number greater than 50%, right? Because we got more than half of this distribution colored in. So we need to find a number. And if we find something that's less than 50%, we know we've done it wrong. So I'll show you exactly what I mean by that. So let's say we put in our mean, 1.98. We put in our standard deviation, 0.87. We plot that distribution. And let's say that we actually made the mistake that I just almost made when I was coloring in. We want a value of 2.6. And let's say that we mistakenly say, yeah, we want to the right of the value. And we calculate that area. And it says, well, your area is 23.8. And we say to ourselves, well, wait a second. We knew from what we drew, it's got to be more than 50, right? So we must have done something wrong. And then you take a look and you say, oh, hang on a sec, that doesn't match what we drew. It's going the other way. So we go back up here and we say, no. It's to the left of the value that we want. You calculate the area. That looks like what we drew. That has a value greater than 50, which is 76.2. So this is now giving us confidence that we did this correctly. So 76.2, we go back to our dean and we say, hey, your students, actually 76.2 of them are in that beneficial zone. So if they wanted to help as many students as possible, you don't need to put a lot of resources into reducing hindrances because 3/4 of your student population is actually in a good zone in terms of that non-beneficial stress. They're in that good low scores in terms of that stress that hinders academic performance and mental health. However, they don't seem to have enough of the good stress that maximizes and increases the performance of students. So rather than trying to alleviate stress wholesale, what you would want to do is you would actually want to make courses more rigorous, have more deadlines, have more exams or projects to do, and that would help increase the student performance by adding that good level of stress. And again, that is something that you can intelligently recommend once you know how to do the work with normal distributions. All right, so that is it for day in the life of being a school psychologist. Any questions about that before we move on to other topics today? All right. Okay, so now we're going to just take a little bit of a detour and talk about how up until now we've been looking at a lot of examples, and I chose these examples specifically because their distributions tend to be normal. But oftentimes in psychology, things are not normal, and you're going to be dealing with distributions that are not normal. So I just want to put that on your radar so that you don't just simply take a distribution and start manipulating it and using a normal distribution to model it if it's not normal. So it's important to be aware of these distributions. Exactly how do we use Distributions that are not normal is going to be answered next time we meet with a little bit of mathemagic known as the central limit theorem. But for now, it's just important to know that not everything follows a normal distribution. So we'll take a look at a couple of really famous examples, things that pop up in psychology all the time. So one of the things that visual scientists have used as a measure of anything from attention to intention to other sorts of cognitive dimensions is eye fixation. So where are you looking? How long are you looking for? How long before you look at something else? So they'll measure eye fixations. And a recent study by Staub et al. Showed the actual distributions. This was great because they actually had pictures of the distributions of word frequency on eye fixation durations. So if a word is a very common word, has a high word frequency, do you fixate on it for longer than words with low word frequency, or do you fixate on it for shorter times than words with low word frequency? What is the relation here? That's what they wanted to answer. But for our purposes, really nicely, they had this distribution of the actual eye fixation times. So we're going to zoom in on a little bit of this. But first, I'll just point out, this is figure 5. But importantly, this is a density function. So we know what that is now. It's a distribution where the area under the distribution is equal to 1. So this will just kind of show you, as you learn more statistics, the stuff that you read about psychology is going to make more and more sense. So that's a density function generated from best fitting X Gaussian parameters. That's grad school statistics, so don't worry about that. For high frequency, that's the HF, and low frequency LF words. So let's zoom in on this a little bit. So here we have the fixations in milliseconds. So how long did they look at that particular word in milliseconds? And then here we have the frequency. You can think of it. So density just is a fancier way of saying the frequency with which those fixations occurred. And we're going to start off with the high frequency words. And what I'm going to point out to you, we're not going to discuss this very much, but what I want to point out to you is that this curve, the straight line there, not the dotted line, but the solid line, that is not a normal curve. And if we take a look at where the peak of that curve is, if it was a normal distribution, it would be symmetrical around its peak. So that's one of the easiest ways to kind of visually take a look and say, well, is this a normal distribution? So if we just take a look at where the peak is for high frequency words, you can see it's there at around 550 milliseconds. But take a look to the left of that and take a look to the right of that. That's not symmetrical. So eye fixations for high frequency words are very, very highly right skewed. So just as a quick mention, the direction of the skew is wherever the tail is. So this is the tail right here. That is to the right. So that is a right skewed distribution. And then we can also take a look at the dotted line, which is the low frequency words. And as it turns out, you tend to fixate longer on low frequency words. But when we take a look at that dotted line distribution, again, we can draw a line down from the peak of that distribution and take a look at both sides of it and see that it is also not normally distributed. It is also very heavily right skewed or skewed in the right direction. So this is just an example. Eye fixations, very commonly used tools. However, the distribution of eye fixations are not normal. So if you knew, for example, the mean of these eye fixations and the standard deviations of these eye fixations, which is something that you could calculate, you cannot go to that normal distribution online resource that we were using to do calculations about this because the distributions are not normal. All right, another example, scores on depression. Depression scores tend to, thank goodness, not be normally distributed in society. So this work by Tomitaka et al., distributional patterns of item responses and total scores on the PHQ-9, which is a measure of depression, the Patient Health Questionnaire version 9. And they also reported frequency distributions. So we are going to focus on the one on the left there. So let's just zoom in on that. So this is the frequency distribution for the total scores. So you take all of the items on the PHQ-9, total them all up, and those are your total scores there. And then we have the frequency, in this time in percentage, in terms of how often they occurred. And this one, if you take a look at its peak is actually right at 0. So the most frequent responses on this PHQ-9 is a score of 0. So that indicates a very low amount of depression. That is wonderful for society as a whole. However, you can take a look at this and very clearly see, well, this is not a normal distribution because it is not symmetrical around that peak value. So once again, we can calculate an average for this distribution. We can calculate a standard deviation, but we cannot go to that online resource and start doing normal distribution calculations on this because they will be false, they won't be true, because this is not a normal distribution. We can't figure out things about this curve by using a normal distribution curve. All right, and the last example comes from a study from the NatSal. So if you recall, a while back we talked about the NatSal when the National Survey of Sexual Attitudes and Lifestyles, when we were taking a look at sampling techniques. And this study by Mercer et al., Changes in Sexual Attitudes and Lifestyles in Britain Through the Life Course and Over Time, they had a very interesting result that took a look at the number of sexual partners. So it was the number of sexual partners, heterosexual, opposite sex partners, that people between the ages of, what do we got here, 35 to 44. So how many sexual partners did people have by the time they were between 35 and 44 years old? And once again, we have our frequency distribution here. So we're going to zoom in a little bit. And on the x-axis here, we have reported number of lifetime opposite sex partners. So that's going to be important in just a little bit. So that's a reported number of lifetime opposite sex partners. And then on the y-axis here, we have the percentage of people who were surveyed with each number of partners. And then it's a little bit more difficult to see here, but we'll break it down. So let's start with the men who are 35 to 44 years old. And the most common number of partners for men 35 to 44 years old, basically the peak of the distribution. So another way of saying peak of the distribution. And just as a real quick aside, this measure of central tendency is actually called the mode. So the mode is just the peak of a distribution. Well, the peak of the distribution for males is one sexual partner. So the most common number of lifetime opposite sex partners that men between the ages of 35 and 44 have had is just one. But you can see that it is not normally distributed, because if that's the peak, it should be, if it was normally distributed, it should be symmetrical on both sides. And it is not symmetrical on both sides. It clearly has a tail going off to the right. So this is skewed to the right. And then also we have for women, what is their reported number of lifetime opposite sex partners? And once again, the most common number for women was also one. So again, we take a look at that mode, we take a look at that peak, and we say, is it symmetrical around the peak? Clearly not, still skewed over to the right. So once again, we cannot use a normal distribution, tables, calculations to figure out what are the proportions in certain areas of this curve, because this curve is not normal. So curve is not normal. And then one other thing that kind of struck me, and again, this is why you always want to take a look at your data, draw out your data. Remember that this was reported number of lifetime opposite sex partners. So they basically, it was a self-report. And as you can see, there's a kind of smooth decrease as you go from one partner to two partners to three partners to four partners. Around 10 partners is still kind of smooth, 11, 12, 13. But then you get to a point where there are these spikes. So we have a spike at around 20, where it was decreasing, 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 and then a whole bunch of people said 20. And then we have another spike at around 30, where it continued to decrease, and then a whole bunch of people said 30. And we kind of have a spike at 35. We kind of have a spike at 40. Does anybody have any idea why we have those spikes at those particular numbers? I'll give you a hint. This is reported number, so this is self-report. All right, I see some people smiling, so you probably figured it out, but you don't want to say it out loud. These are examples of individuals, at least a lot of those individuals, if you just base it on the shape of the curve, those were individuals that were estimated. So those are the individuals that lost count and kind of knew, you know what, it's around 20. So maybe it's 22, maybe it's 19, maybe it's 23, but they couldn't remember the exact number. So we have a tendency when we're reporting things that we're unsure of to report round numbers. So the people that said 30, could have been 28, could have been 29, could have been 32, but they were like, you know what, it's kind of, I can't really remember everyone. I would estimate it's around 30 or 35 or 40. And this is something where I really want to be very, very careful in not imposing any sort of judgment at all on these individuals. But I would find it a little bit weird, just to be fully transparent here. I would find it a little bit weird if somebody did not give me a round number and it was high. So if somebody said, what was the number of lifetime opposite sex partners you had? And they were like 41. I know that person has a bedpost somewhere with notches on that bedpost. And they went to it and just started counting. They were like, how many do I have? 41. Okay, perfect. Or just took a look down at their belt and said, how many do I got? Oh yeah, 41. So that seems a little, those are the people, you can see some of them, those are the people I would want to interview and just figure out what was it how did you get that number? But importantly for our purposes, not normally distributed, can't use that normal distribution tools that we were developing. So lots of things are normally distributed, but not everything is normally distributed. So keep that in mind as we go forward. All right. So now we're going to get to the new kind of like really important part of today's class, which is sampling distributions. And we are going to introduce this idea of sampling distributions today. And then we're going to work with the idea of sampling distributions next time. And then everything that we do going forward from here in inferential statistics will use sampling distributions in some way. So this is a very, very important concept. Stay with it for as long as you need until it kind of sinks in, until you can go that 3 levels deep on that distribution inception. It'll be worth the mental effort. So let's start off real simple with just the idea of statistics and parameters. So these are two very, very different things. So a statistic is a number that describes some characteristic of a sample, such as the mean of a sample or the standard deviation of a sample, right? It's a number that describes a characteristic of the sample. How many people are in the sample, right? Those are all statistics. And we need to very clearly differentiate those from parameters. And parameters are numbers that describe some characteristic of a population. And the reason that these two sometimes can get confused in our mind is because what we do in inferential statistics is we use a statistic because that's what we have, right? So we can actually measure statistics. We can measure the mean of a sample. We can measure the standard deviation of a sample. We've done that, but we don't want statistics. What we want is parameters. We don't want to just be able to say things about a sample. We want to be able to say things about a population. So what we do in inferential statistics is we use that statistic to try to estimate parameters. So it's important because we're using a statistic to stand in for a parameter. That's basically what inferential statistics does. We don't want to forget that they're two separate things, that we have access to the statistics. Those are the things that we can actually calculate: sample mean, sample standard deviation. And we use those to estimate the parameters. Those are things that we can't measure: population mean, population standard deviation. You're never going to measure 7 billion people on Earth, just because even if you had the resources, people would drop out of the study. You never get parameters. We get statistics. We try to use them to estimate parameters. So why is this so important? is so important because the ability to go from a statistic to a parameter is what gives psychology its power. It's what makes psychology something for the people instead of something for the elites. So let's just go back to our example about the remedial program. So let's say that we have this remedial program and we actually institute it. So the dean of this school, he says, you know what? I liked your analysis. I think it's a good idea. Let's start this remedial program. We'll put the 50 students in the remedial program. So here are those 50 students. Some are happy to be there, some are not. They go through the remedial program and the dean comes back to you, calls you back into his office and says, hey, it was a massive success. Our 50 students improved their mean IQ scores by 9.4%. That's a massive increase, right? The average increase was 9.4%. What this means is that you have a program here that is amazingly effective, but without inferential statistics, all that you know and all that you can say is that your program worked for these 50 students. Your program increased their IQ by 9.4. And that would be it. And it would be for these 50 students and these 50 students alone. And you would try it again next year and maybe it would work, maybe it wouldn't, but there would be no way to take it to the masses. What inferential statistics allows you to do is it allows you to take a look at this sample of 50 students and then objectively, intelligently, with a algorithmic procedure so that our own biases don't get caught up in our inferences. It allows you to say, well, wait a second, based on the data we collected, this program is not only going to work for these students in this school, but it'll work for these students in the neighboring school. And it'll work for these students in the neighboring city. And it'll work for these students in the neighboring state. And it'll work for these students in the neighboring region. And it'll work for students around the world. So based on our sample, we are able to infer that it is going to work for students all over the world. And you've just taken your impact from 50 students to potentially every student in the world. So hopefully that gives you an idea of exactly why we're doing what we do in statistics and why it's so important to be able to go from a statistic and estimate that parameter, but do it in an intelligent way that takes our own bias out of the equation. Because we developed the program. Of course we want to take it worldwide. We think it's great. We wouldn't have given it to the dean if we didn't believe in it. We need a way to make sure that we can remove that bias and use statistics to estimate those parameters. Will this actually work for the world? All right. So now that we kind of introduced the idea of bias, human bias, we're going to talk about bias as it refers to sampling distributions and a sample being used to estimate parameters of a population. So when you take a sample, you have what is known as bias, and you have the potential for what is known as variability. So what a bias is, when we're talking about a sample and sampling distributions, a bias is how likely your sample is to underestimate the value that you want to know about your population. So bias is how likely is it that your sample is going to underestimate the population you want to know about, or how likely is it that you're going to overestimate the value that you want to know. So bias always moves in one direction. Either you have a bias towards overestimation or you have a bias towards underestimation. You can't have a bias towards both. We'll see why in just a little bit. So a statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the value of the parameter being estimated. We're going to see what this means in just a moment, but I just want to draw attention to the fact that it's based on the sampling distribution. So it gives you an indication of how important that sampling distribution is. So that's bias. What about variability? Well, variability is how spread out is your statistic. So when you take your sample, if you took your sample over and over and over again, how spread out would those sample means be? And you can see in that language that I just used, if you take your sample over and over and over again, if you make a distribution of samples, then you can figure out your variability. So the lower the variability of the sampling distribution of a statistic that is used to estimate a parameter, the lower the average sampling error. So the lower the error between what your statistic says and what your parameter actually is. All right, so just to kind of visually give you a reference of what this will look like, this is from your textbook. So if you have a sample, what you're trying to do is almost like you're throwing darts at a target, and your sample is each dart that you throw. So one dart would be one sample, another dart would be another sample. And the worst case scenario is a scenario like this. We're trying to hit the center of this bullseye. That's the actual parameter of a population. So that's the population mean, or that's the population standard deviation. If your sampling techniques have high bias and high variability, that means that your high bias means that you're not near the target, you're off to one direction away from the target. So in this case, we're off to the upper right. And also your variability is high, which means that your darts are all spread out. And that's the absolute worst situation that there is. The second worst situation is if you have high bias, but you have low variability. So now we have a very tightly grouped cluster of sample means, for example. We have a very tightly grouped cluster of statistics, but they're not where we want them, right? That's a high, the bias is high, it's far away from the target, even though now they have low variability, they're very precise estimators. So this is the second worst scenario, because again, we're not estimating what we want, that bullseye for the population. All right, now we get to the first case that is useful, that is actually not a bad situation. So this is where you have low bias, but you have high variability. So in this case, you're gonna be off. That's the high variability. You're not gonna hit that target very often. However, importantly, you're not biased in any particular direction. You're not overestimating the population mean, you're not underestimating the population mean in a regular systematic way. So in this case, over time, as you repeat experiment after experiment after experiment, you'll kind of see where that population mean is. So this is useful if wasteful of resources, because you need to take sample after sample after sample after sample. The best situation is if you have a sampling technique that gives you this, where you have no bias and you have low variability. So you're hitting the bullseye, and not only are you hitting the bullseye, but every single sample is basically hitting the bullseye. So you don't need to take a lot of samples. You don't need very large samples to get to that low variability. And that allows you to very accurately estimate what is the parameter from the statistics that you measure. All right, so I promised visuals. We're gonna get some visuals. So this is, now we're gonna go through two demo callbacks. So these demos we've seen previously. We talked about it a little bit, but now I'm gonna point out the sampling distributions that were used in each of these demos. So the first demo here, I'll read it out. So an airline has just finished training 25 pilots. This is the pilot demo from class number 2. So they've just finished training 25 pilots, 15 male pilots and 10 female pilots to become captains. Unfortunately, only 8 captain positions are available. Airline managers announced that they will use a lottery to determine which pilots will fill the available positions. They write the names of all 25 pilots on identical slips of paper. They place the slips in a hat, mix them thoroughly, and draw them out one at a time until all 8 positions are filled. A day later, managers announced the results of the lottery. Of the 8 captains chosen, 5 are female and 3 are male. Some of the male pilots who weren't selected suspect that the lottery was not carried out fairly. They wonder if there may be grounds to file a grievance with the pilots union. Is it plausible, believable that 5 females could be selected by chance alone? So for this, we're going to go back to the Statlet resource, but this time we're going to take a look at hiring discrimination. It just won't fly. So if you want to follow along, if you want to do this with me as I go, you can go to that application as well. And what we have here is we have a representation of the 15 males. So each of these is one of the males, and we have the 10 females right here. And what we're going to do when we generate a sample is it's going to randomly select from these 25 pilots. They're going to randomly select from these 25 pilots, 8 of them. And it's going to calculate how many of those 8 pilots are female. So let's generate our first sample here. So we just go to generate sample. And what it does here is here we have our sampling distribution. So we have the number of females selected, and it can go all the way from a low of 0, no females were selected, to a high of 8. 8 females were selected out of 8. What did I just do? There we go. 8 females were selected out of the 8 captain positions available. And what we see here is that for our first sample, the number of females selected was 4. Now, normally in the real world, this is where you would end, right? Normally you would take the samples out of the hat, you would choose who was going to become a pilot, and you would say, there's 4 females. All right, let's go tell them the good news. But to give you an idea of a sampling distribution, what a sampling distribution is, it's a distribution of every possible sample that could have occurred. And then it gives you a frequency distribution, in this case, of how many of those samples had a certain number of female pilots. So we can simulate that by taking a look at this frequency distribution here and building a sampling distribution by just taking another sample and adding it to our frequency distribution. So we can just hit generate sample again. And now we see that we have a second sample, a new random grabbing of pilots, and now we have 4 females again. And we can continue to build our distribution, generate sample. We have another random sample with 4 females, generate sample. Now we have a new random sample, and this time there's 5 females. So now we're starting to see a distribution start to build. And we can hit generate sample. We have a new sample with 3 females, and you can do this over and 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 over. And you can see that we are now starting to build up a dot plot of our distribution, right? We're starting to build up our distribution, and we can see that 3 and 4 tend to happen a lot. So 3 and 4 females tend to get chosen often, 5 females kind of rare. We have no samples with 6, 7, or 8 females yet. We have a couple with 2 females, no samples with 1, no sample with 0. But importantly, these are all samples that are possible. And we continue to generate samples. And what we're building up is a sample distribution. This is a sample distribution of the number of females in this case in each sample that we take. And the more samples we take, the more this distribution tells us of all the possible samples that we can have. Now, I highly recommend give this a shot, try it out. And then one thing that you can also do is go down here to the quick add, and you can add a bunch of random lotteries so that you don't have to press this button over and over and over again. So let's just go to the max. Let's add 2,000. We'll max it out right at the beginning. And then we hit go. And we can see now that we have very skinny lines, but we have a distribution here. And we can see that it's very rare that we had 0 females. It did happen, but it was very rare. Most often, we had 3 females chosen. And then slightly less often 4 and 2, and then it tapers off. It's skewed to the right over here. I don't think we actually got any samples where there were 8 females. But this is looking more and more like a distribution that we are familiar with. This is looking more and more like a normal distribution. And we're going to see why next time. Incidentally, the average number of females, if you did this a bajillion times and then calculated the average would be 3.2. So the average number of females that you can expect on average in this scenario is that 3.2 females would be chosen as captains out of the 8 positions available. And that is something that, again, you can see here. If we were to calculate the average, it would be right here at that 3.2 level. So again, this is a distribution, just like the distribution that we've been using up until this time. But importantly, each of those dots, let me just redo this. Each of these dots is not an individual, it's a sample. It's a single sample. And when you generate a distribution, do not forget that each of these dots here is not an individual, it's a sample. And that's what makes this a sampling distribution, because it's a distribution of samples. So all the normal distributions that we've been looking at so far, those have been distributions of individuals. That's one kind of distribution. This now that we're looking at right now, this is a distribution of samples. This is a distribution of a sample of 8, and it measures how many females are in this sample of 8. So don't get the two confused. These are not individuals. These are samples. This one has 3 females. This one has 4 females. All right. So that is our first brush up against sampling distributions. Any questions on that? Does it kind of make sense? Sinking in a bit? Yeah? Okay. So the other one that we're going to revisit is the sunflower example. So for this one, we can go to the sunflower statlet. So sampling sunflowers right there. And I'll reread the scenario. So a British farmer grows sunflowers for making sunflower oil. Her field is arranged in a grid pattern with 10 rows and 10 columns as shown in the figures below. Irrigation ditches, 10 rows and 10 columns we have here. Irrigation ditches run along the top and the bottom of the field. So that's this blue strip here. That's one irrigation ditch at the top, one irrigation ditch at the bottom. The farmer would like to estimate the number of healthy plants in the field so she can project how much money she'll make from selling them. It would take too much time to count the plants in all 100 squares. Can't measure the population, right? Can't measure the population of plants. So she'll accept an estimate based on a sample of 10 squares. You can measure the sample. You can get the statistic, can't get the population. So we originally came here to take a look at what sampling method will give her the best estimate. But what we're going to do now is we're going to see 2 different types of sampling distributions. So what I want you to do, if you want to follow along and do this as I do it, first thing we're going to do is we're going to go here to this simple random sample. And just to refresh your memory, a simple random sample is where we're going to choose 10 squares, and it's going to be completely at random. We just choose 10 out of the 100. There's no pattern to it whatsoever. So to do that, we're going to click Generate Sample. And it generates a sample, and the X's here are the random squares that this sample chose. So first off, notice that random oftentimes to humans does not look random. I mean, we got 1, 2, 3, 4 plots in this final column here, but this is a random selection. So we're going to do that for this one here. And then we're going to scroll down here to method 2, stratify by row. And stratification, again, is where you split your population up into different strata. In this case, we're going to split them up into rows. And then you do random selection within that strata. So what that does is it will guarantee, if we click Generate Sample here, it guarantees that there is 1 square in each row. That's what stratify by row does. And then to use this applet, we're actually going to have to stratify by column, but we're not going to use the stratify by column in the final analysis. So we can just hit Generate Sample, and we'll move on down here. If we did a census. If we did a census means if we measured the population. Very rare that you can ever do that. But if we were able to measure the entire population of sunflowers, if we gave her unlimited workers and said, hey, you can have as many workers as you want, they can count all 100 plots of land, we could do a census, and if we click on Reveal Results, these are the numbers of healthy plants in each of the rows and each of the columns. Right? So in each plot of land, these are the numbers of healthy plants. Notice here that the mean, the actual true mean number of healthy plants is 102.46. So that's the mean number of healthy plants. And now we can go back up here to the simple random sample, and we can build our sampling distribution. Because right now we have one sample, the sample right here. And it is telling us that it is the average number of healthy plants is 102.2. So we have a little bit of sampling error, right? Because it's 102.46, so we're off by 0.26, a little bit of sampling error. And maybe we're biased, maybe our sampling technique is biased towards underestimation, but you really can't tell with just the one sample. So what we do is we create a sampling distribution by generating a new sample. So we click on generate a new sample, and now notice that we have a new sample over here with a mean of 103.4. So our first sample underestimated a little bit. Our second sample is overestimating by a little bit more. And then we can hit generate new sample and generate new sample. And each of these dots here is the mean of a new sample. So this is going to be a distribution of sample means, or in other words, a sampling distribution. So again, these are not individual plots of land. These are not individual sunflowers. This is the average number of healthy plants in 10 randomly selected plots of land. So we can continue to build this up, and we build it up, and we build it up. And what you'll notice, first off, is that we have what is known as an unbiased estimator. Because some of these sample means, they're below the actual average, the true mean average. Some of them are above the true mean average, but they don't tend to be above the average, and they don't tend to be below the average. They're basically spread out evenly above and below, so it's not biased. So remember before I said if you have bias, you only have it in one direction. You're either biased towards overestimation or you're biased towards underestimation. You can't be biased in both directions because that just evens everything out and balances everything out. So we actually have this thing being unbalanced. Sorry, unbiased. It's balanced, so it's not biased. All right, but it's pretty spread out. Now if we go down here to stratify by row, we built up this sampling distribution, and we can see that it's highly variable. It's not biased, but it's pretty variable. Now if we go down here to where it says stratify by row, we have our first estimate, 102.6, overestimated by a little bit, but we can't tell anything from just that one sample, so we can generate a new sample. And this new sample, 102.8, also overestimated a little bit. And we continue to generate samples. And now we have some that have underestimated the number of healthy plants. We have some that have overestimated the number of healthy plants. Importantly, each of these dots is a new sample. It's the mean of a new sample. And we can build, by generating new samples, this distribution of samples, this distribution of sample means. And one thing that you'll notice, if we just kind of keep building and building and building, well, two things that you'll notice. Number one is that we have another unbiased estimator. So we have some values that fall below the true mean. We have some values that fall above the true mean, but it doesn't tend towards overestimation and it doesn't tend towards underestimation. So it's not biased. It's a true estimator of the actual population mean, the parameter that we're interested in. And importantly, in terms of variability, this stratified by row sample is much less variable than the simple random sample technique. So we mentioned this when we looked at sampling techniques earlier, but now you can see it once again with a new perspective. In this case, for the simple random sample, we have an unbiased estimator with high variability. In this case, with the stratified by row samples, we have an unbiased estimator with low variability. So in this case, we would want to pick the stratified by row sampling technique because it gives us a true measure or a true estimate of the population parameter, but we know that on average, we're going to be off, but not by much. We're going to be off by a little bit. Whereas if we did it by a simple random sample, we might be off by quite a bit. And then what we're going to do down here, just real quick, is we're going to say, all right, to the simple random sample, quickly add, let's do 500 of these. And we're going to hit go. And then they generated the data. And then to the stratify by row, let's also add 500. And we'll hit go. And now let's see what that did to our sampling distributions. So let's scroll all the way to the top here. So it's kind of harder to see here with the simple random sample because it is so spread out. We might have wanted to add some more samples to this, but we'll scroll down here to the stratify by row where it's a little bit more visually obvious. So here we have a sampling distribution, and notice that this sampling distribution is looking very, very familiar. It's kind of got that bell-shaped curve, right? A lot of the sample means fall really close to the true mean. Some of them fall further away, but as they go further away, the frequency with which they occur goes lower. As they go further away, underestimating, the frequency with which they occur goes lower. So this is looking a lot like a normal distribution. And that going forward is going to be very, very, very important, because what we have here is a way to use the normal distribution in almost any situation. And to show you what I mean, let's go back to the sunflowers. So just real quick. So I took all of these values here and I put them in a frequency distribution. So that's the population of healthy plants. And I put them in a frequency distribution. And what that frequency distribution looks like is this. That's the frequency distribution of all the healthy plants. And if you take a look at the mean, which is right about there, that frequency distribution, that's not a normal frequency distribution, right? That is not normally distributed. If anything, it's bimodal. There's two peaks. It's heavily skewed to the right. It's not a normal distribution. And if we had to do calculations on the population of plants, we would be really, really at a disadvantage. We just couldn't do it without measuring all the plants, without measuring all of the, without figuring the frequency of all of the population. We couldn't do it because we would have to know the shape of that frequency distribution. And it's a weird shape. And it doesn't have anything that we have any sort of knowledge of. However, and this is where the math and magic comes from, that's the distribution of the population. And it was not normal. So we could not use any of our normal distribution techniques. But if you take a look at the distribution of samples, the sampling distribution, that sampling distribution is normal. And if it satisfies certain conditions, it gets to be more and more and more normal. So what we're going to see next time is that the sampling distribution is what allows us to go into any population and say, I can help this population. I can do psychology for this population. And I don't need to know what the distribution is in the population. So I can help out people suffering from depression. And I don't need to know what the distribution is of people suffering from depression. And I can help out people with addiction issues. And I don't need to know what is the distribution of, whatever I'm measuring with people with addiction issues. People that, suffer from childhood trauma, people that suffer from broken relationships, people that suffer from anything you want to help them with. You don't need to know that population distribution, because as soon as you take a sample from that population, it doesn't matter what the population looks like. It doesn't matter at all. As soon as you take a sample from that population, as soon as you say, you know what, I'm going to study 30 of you. I'm going to take 30 of you and I'm going to do a study on you to figure something out that can help everybody. As soon as you take those 30 people, you have a sample. And as soon as you have a sample, you have a sampling distribution. As soon as you have a sampling distribution, you have a normal distribution. And once you got a normal distribution, you can do everything that we learned with that normal distribution. So this sampling distribution idea is also what takes psychology from being only for the elite who can afford to pay for studies to benefit probably themselves, and it gets to be for everybody. As long as you can take a sample from that distribution, if you got the funds for that, you can figure out the sample, you have a normal distribution, you can help the population. All right, so that is just about, let's just put a pin in it before we wrap up. So as you can see, of the 4 conditions here, the simple random sampling technique That gave us low bias, but very high variability. However, the stratified by row technique, that gave us no bias and very low variability. So we would want to always choose, if we can, the ideal situation, no bias and low variability. But yeah, that is our intro to sampling distributions. So I highly recommend try out those applets on your own, see if you can play around with it, kind of see it build. It really helps you to understand what's going on. Because as I said, we're going to start taking a look at sampling distributions, and you're going to have the distribution of the population, that's level 1, the distribution of the sample, that's level 2, the sampling distribution, which is the distribution of samples, that's level 3. So the more you can keep those separate in your mind and realize that they're the 3 different concepts, the more sense inferential statistics is going to be. It takes a little bit of practice, but hopefully this intro has started you down that road. And I think this intro will be wrapped up right here. So that's all I wanted to cover for today. Thank you for coming by.